In the last video, we implemented all the mathematics we need to draw an accretion disk around a black hole. In this video, we'll do the visual appearance of the disk. To start, we'll investigate the temperature distribution of the disk. Then we'll look at thermal radiation to calculate what the color of the disk is. The temperature distribution in an accretion disk can be described by this function. I know I'm just passing this function from the high heavens here, but I don't want to do a full derivation of this. Apparently, it's pretty doable to derive the value of these exponents, but getting a good estimate on this value in front is apparently quite complicated. This kind of equation is often called a scaling relation, as it describes how a quantity, in this case the temperature, scales with respect to other quantities. Scaling relations are often written in this form, where you have a value in front multiplied by different quantities, and each of those quantities is divided by a typical value and then raised to some power. This may sound a bit vague, so let's go over each of these factors and see what this means for our temperature. First off, we can see that the temperature scales with r to the power of minus 3 over 4. So the further we go out into the disk, the lower the temperature is. Makes sense. Rs is a Schwarzschild radius, which is 2gm over c squared, and remember we are using geometrized units, where g and c are 1, so this is just 2m. Next we have the mass accretion rate, to the power 1 over 4. So for higher mass accretion rate, we have a higher temperature. I think this also makes sense. If we throw more stuff onto the black hole, we would expect things to get hotter. Here we divide by 1 solar mass per year, which is a typical value for active supermassive black holes, the kind of black holes we find in the center of galaxies. So this is just a way to say the mass accretion rate in solar masses per year raised to the power 1 over 4. Then we have the mass of the black hole itself, to the power minus 1 over 2. So the more massive the black hole, the cooler the disk. That is not something we would expect beforehand. Again, we divide by a typical value for supermassive black holes, which is 100 million solar masses. The reason for putting in these typical values for mass accretion rate and total mass is just to be able to use values relatively close to 1 in our shader, instead of having to put in values on the order of 100 million. Finally, there is this f of r. This is a function that goes to 1 for large values of r and goes to 0 as r approaches 6m. This is a relativistic effect. Massive particles cannot have a stable orbit below a radius of 6m. For this reason, this radius is also called r-ISCO, for innermost stable circular orbit. I'm not quite sure how this influences the temperature of the disk, but apparently there is this effect of the temperature dropping near this radius. We don't quite know what this function is exactly, but we'll make something up later. One thing I'd like to note here is that this equation is derived for an optically thick, geometrically thin disk. Optically thick means you can't look through the disk. In reality, however, this is often not the case for accretion disks. Geometrically thin means a disk is considered to be razor thin to a good approximation. Also, this doesn't have to be the case for disks in real life, they can have a variety of shapes. Although I think for accretion disks around black holes, this is usually a good approximation. To describe optically thin and/or geometrically thick disks, you need to do a full simulation, which is very complex and computationally expensive. And by expensive, I mean like let it run on a supercomputer for a week kind of expensive. People have done these kinds of simulations though, and it turns out that in these less idealized situations, the temperature usually still follows this kind of relation, but with slightly different powers for r, typically between -1 and -1/2, depending on the properties of the disk. So what we can do here is to make this power of r a free parameter, to have some more artistic control. Filling in some typical values, we can see that for supermassive black holes, the disk reaches a temperature on the order of tens to hundreds of thousands of Kelvin, or degrees Celsius. At that point there's no difference anymore. A stellar black hole, the kind of black hole that is left behind by a massive star when it dies, has a mass on the order of 10 solar masses. Accretion disks around those kinds of black holes are much hotter, with temperatures reaching hundreds of millions of Kelvin. It's hard to appreciate what these large numbers actually mean physically, but I'll try my best to give you some insight on that in a minute. First though, we need to introduce blackbody radiation. We all know that hot things start to glow. In fact, all material emits light just from having a non-zero temperature. It's just that past a certain temperature that light enters the visible part of the electromagnetic spectrum. The radiation emitted by material purely caused by its temperature is called blackbody radiation. Blackbody refers to the idea of an object from which you receive only its thermal radiation, so no reflected light from somewhere else or anything like that. The spectrum of blackbody radiation is described by Planck's law. Here h, c and kb are constants, so this function describes, for a given temperature, what wavelengths of light are emitted by the material and how much. Here you can see that function plotted for different temperatures. You can see that for hotter temperatures, the curve becomes higher and shifts to shorter wavelengths. In other words, hotter stuff emits more light and bluer light. One key feature of Planck's law is that the total amount of energy emitted by a blackbody is proportional to the temperature to the fourth power. This is the Stefan Boltzmann law. It means that if you have two identical objects, A and B, but A is at twice the temperature of B, it will radiate 16 times more energy per unit time. If A were to be 10 times hotter than B, it would radiate 10,000 times more energy. Now might be a good moment to think back of what we just said about the temperature and accretion disks of black holes. Material that is hundreds of thousands of Kelvin or even hundreds of millions of Kelvin emits a very large amount of light. In fact, 1 square meter of a blackbody at 300 million Kelvin emits about the same amount of light as the entire sun. This is how stupidly luminous accretion disks are. This is why accretion disks of supermassive black holes can outshine their entire galaxy of hundreds of billions of stars. This steep increase in luminosity is going to be a problem for us. If we wanted to represent the brightness of the disk accurately, we would either have a white screen or see just a relatively thin ring of the hottest part of the disk. Even though this would be physically accurate, this doesn't necessarily make for a good looking black hole. So this is where we'll have to cheat a bit, and deviate from trying to be 100% physically accurate. What we can do accurately though, is the color of the light. We can now describe the spectrum of light emitted from hot material, but in computer graphics we don't work with wavelengths of light. As you probably know, colors are described using a red, green and blue component, and using different amounts of red, green and blue produces different colors. This means that we cannot directly use what we just derived in our shader. We need some way of going from a distribution of wavelengths of light to RGB components. To do so, we need to introduce the concept of filters. Physically, filters are thin sheets of material that allow some wavelengths of light to pass through and block others. On top of that, not all wavelengths that do pass through do so at 100% efficiency. Some wavelengths are, for example, blocked for 50%, others are only blocked for 10%, letting 90% through, and others are almost completely blocked, letting only 5% through. A filter is defined by its spectral sensitivity profile, which is a curve that specifies which wavelengths pass through at what efficiency. You can, for example, define a broad red filter that lets through a wide range of red light, but blocks everything else. Or you can define a shallow blue filter that only lets through a small range of blue wavelengths and blocks everything else. Let's look at how we can mathematically describe what a light source looks like through a filter. Say we have a light source with a spectrum which is typically denoted with I of lambda. To get the total luminosity of the source, we can integrate the spectrum over all wavelengths. Now when we look through a filter, we don't see all wavelengths. Let's say we are looking through a filter with a spectral sensitivity profile S of lambda. For a certain wavelength, the amount of light we see is the emission by the source multiplied by the sensitivity. So the total luminosity of the source, as seen through the filter, is found by integrating I times S over all wavelengths. In practice, we have a lower wavelength lambda 1, below which the filter is fully opaque and blocks all light. And similarly, there is an upper wavelength lambda 2, above which the filter blocks all light. This means we don't have to integrate over all wavelengths, just those between lambda 1 and lambda 2. Our eyes have 4 kinds of light receptors, each with a different filter. One has a very broad filter, which lets through all visible light. These receptors are the most sensitive, but cannot discriminate between colors on their own. As a side note, this is why when it's dark and there's just enough light to see, you see everything in black and white. There's only one type of receptor in our eyes that is sensitive enough to see with such little light entering our eyes. The other three types of receptors in our eyes are only sensitive to parts of the visible spectrum. It is these three types of receptors that lets you see color. The fact that we have three kinds of color-sensitive light receptors in our eyes is precisely why we can represent colors as a combination of red, green, and blue. More than 90 years ago, in 1931, the spectral sensitivity profiles of these three receptors were quantified and published as the CIE XYZ standard observing color matching functions. Funnily enough, our red receptor is also sensitive to a part of the blue end of the spectrum, which is why we see wavelengths of around 400 nanometers as violet. These curves thus show for each of the three kinds of receptors we have how sensitive they are to the visible wavelengths. Now you might have noticed this says XYZ and not RGB. This is because there is no one way to map these XYZ values to an intensity of red, green, and blue light. First off, we haven't defined yet what red, green, or blue light means. Do we take one wavelength for each of them? If so, what wavelengths? We could also take light sources that emit a small range of wavelengths. How you define red, green, and blue light determines how X, Y, and Z are mapped to R, G, and B. This is where color spaces come in. Over the years, many of such mappings have been defined. Now you might wonder, if we can represent any color with red, green, and blue lights, why can't we just find a good way to map XYZ to RGB and call it a day? The answer is, you've been lied to your entire life. Okay, that may be a bit dramatic, but it is actually impossible to represent all colors using a red, green, and blue component. Whichever definition of red, green, and blue light you choose, there will always be some colors you cannot represent correctly. Typically very saturated cyanes, for example, are notoriously impossible to represent. For those that are thinking of their high school course of linear algebra and are wondering why you wouldn't be able to create a transformation from one vector space to another, the underlying problem is that you cannot create a negative amount of light. Anyway, I didn't want to enter the infinite rabbit hole of color spaces, so I went for the original definition of RGB, the CIE RGB color space. This is a linear transformation from XYZ defined as follows. In terms of color coverage, this is the worst widely adopted color space out there, but for our purposes it should be fine. Using these transformations, we can convert XYZ to RGB. So we want to create a texture containing the R, G, and B values for different temperatures. Since these are three functions of a single quantity, we can do the same as what we did for the turning point in the previous video, stacking the 1D array of values into a 2D texture. The only difference is that we now have three functions, so we'll be using the R, G, and B channels separately instead of having a grayscale image. 64 by 64 pixels should again be more than sufficient. As discussed before, what we need to do is calculate the blackbody spectrum at a certain temperature, multiply by the X, Y, and Z filter respectively, and integrate over all wavelengths. Looking at our code, we start by bringing in the CIE XYZ filters, and defining some physical constants. Then we make a function for the blackbody spectrum. We define a wavelength range and a temperature range, and calculate the XYZ curves as a function of temperature. Finally, we convert XYZ to RGB using the appropriate linear transformations. This plot shows the R, G, and B values for the temperature range we defined in our code, so between 500 and 1 million Kelvin. The axes are in log scale for two reasons. First, you can see that even though the temperature spans about 3.5 orders of magnitude, the intensity spans about 27. Secondly, you can see that for high temperatures, these curves approach straight lines, meaning the intensity scales with the temperature to a constant power. This power can quite easily be proven to be 2, but I won't do it here since we would get sidetracked too much. For those who are already familiar with Blackbody radiation, simply consider the intensity at a single wavelength, and combine Wien's displacement law, the Stefan-Boltzmann law, and the Planck curve in the Rayleigh-Jeans limit. The point is that even though our texture only contains temperatures up to 1 million Kelvin, we can extrapolate for higher temperatures using the last pixel of the texture and using the fact that intensity scales with the temperature squared in the high temperature regime. We don't really need to extrapolate towards lower temperature because the intensity is already pretty much zero at 500 Kelvin. One last thing. Images cannot contain negative values. Well, at least TIFF files can't, maybe there is some other format that can. In any case, you can see here that the intensity goes to 10 to the minus 8, almost 10 to the minus 9. So if we're saving the logarithm of the intensity, this is a problem. We need to add a constant to our image, such that we have no negative values. I chose to add 10. In our shader, we then need to subtract that value from our texture before using it. So in our code, we fill in the texture with the logarithm of R, G, and B, plus 10, and then we save it. In Unity, we bring in our texture and make sure the right settings are applied. Generate bitmaps is off, wrap mode is clamp, filter mode is point, max size is 64 and no compression. Let's start with the disk temperature. We start with 860,000 Kelvin. Then we add the R dependence. For this we start by dividing R by 2m. Then we raise that to a power between minus 0.5 and minus 1. We want this power to be a parameter. We'll call it temperature falloff. Next we have the mass accretion rate to the power of 1 over 4, and the total mass to the power of 1 over 2. Finally we have the ISCO falloff, the relativistic effect where the temperature goes to 0 at R equal to 6m. I came up with this function, which has a parameter for the sharpness of the falloff. Combining it with the radial dependency of the temperature in the disk looks like this. To implement this in the shader, we subtract 6 from R, multiply that by minus 1, divide by the ISCO cutoff smoothness parameter, take the exponential of that and do 1 minus that. Finally, we clamp this between 0 and 1. Next up is the blackbody color. This will be similar to the turning point subgraph since we do the same kind of stacking. So I'll just duplicate the phi-tp subgraph and adjust it. This time you have the temperature as input parameter, and we return the color, which is a vector 3. For our UVs, we take the log of the temperature and map that from the range 2.66 to 0 to 4095. Then we replace the texture with the blackbody color texture and choose the RGBA channels. And we do the same down here. Instead of all of this, we subtract 10 from our texture and do 10 to the power of that. Finally, we need to take care of temperatures outside the range of our texture. First, the low temperatures. This can be easily done by mapping the temperature from 500-600 to 0, 1, clamping that between 0 and 1, and multiplying the texture by that. This will make sure the color is black for temperatures below 500 Kelvin. Technically, the color will be slightly wrong for temperatures between 500 and 600 Kelvin if we do this, but I am fine with that. For high temperatures, we take the last pixel of the texture and take the temperature divided by 1,000,000 squared and multiply those two. Then for temperatures above 1,000,000, we use this instead of the texture. Finally, we make a subgraph for the disk color. We start with the disk temperature. Then we convert that temperature to a color using our blackbody color subgraph. As we said earlier, we want to control how much the temperature influences the intensity. Even though this is not physically accurate, it gives us a lot of artistic control. To do this, normalize the blackbody color and take the length as well. Then we take the length to some power and multiply that by the normalized color. If this power is 1, we get our original physically accurate intensity. If this power is 0, the temperature does not influence the intensity at all. So let's add a parameter called temperature brightness influence, clamp it between 0 and 1 to be sure, and connect it to the power. Finally, we want to control the brightness itself, so we'll add another parameter for that. Since the intensity can span multiple orders of magnitudes, it is more convenient to have the brightness in log scale. So we take 10 to the power of this brightness and multiply that by the color. Currently, the disk goes to infinite R, even though at large R it is way too faint to see. But you may want to have a disk that only goes to a certain radius. We can add this to the shader to have some more artistic control. What we'll do is multiply the brightness with a function that creates a smooth cutoff at some radius. I again played around with some functions and came up with this function, which asymptotically goes to 0 for radii larger than the outer radius, and goes to 1 for radii smaller than the outer radius. It looks a bit like a scaled and displaced version of a simple arctangent, but it falls off to 0 and goes to 1 a bit faster. So we'll add a parameter for the outer radius and the outer radius falloff, implement our fancy function and multiply it by the color. Over in our main shader, it is simply a matter of connecting everything and creating a parameter for every parameter of disk color. We now have quite a few parameters in our shader, so let's organize these a bit. I forgot to remove the little visualization we did in the last video, so get rid of this here. The result looks like this. We have a bunch of parameters we can change to dramatically change the look of the accretion disk. That's it for this video. Thank you for watching and I hope to see you in the next one.